This is Chloe. She's a young entrepreneur, and she founded a startup called New Venture. Very creative name, right? And New Venture helps doctors to summarize their patients' medical history. They do that with AI, of course, with LLMs, because that's the cool thing to do today. And Chloe is shipping fast. She wants to innovate fast, so she's using OpenAI as the backend for her LLM. And 3 months in, one of her potential customers, one of the doctors, asks, "But what happens to the data of my patients? Where does it go?" And Chloe was like, "Oops, it's going across the Atlantic." Game over for her. Chloe was very sad. And she talked to Dr. Snuggles, which is her dog that you can see here. They were brainstorming together, how can we find solutions to this problem? And of course, the right solution was to host LLMs herself. And what do we need to host LLMs? So that was their great idea. What do we need to host LLMs? Well, we need big servers with lots of GPUs. And of course, Chloe had a bit of savings because she had been working as a waitress. So she bought a couple of big servers with a bunch of H100s. And what do we use to manage these workloads on different servers? Of course, we use Kubernetes. Also because those models, the LLMs, they are getting bigger and bigger. They very quickly exceed the capacity of just one machine, right? Now, why am I telling you all of this? My name is Lena, and I'm a cloud native engineer at Bespinian. We help our customers migrate their workloads onto Kubernetes and using AI. But back to Chloe. So Chloe pulled an all-nighter to actually implement this, to actually get GPUs into her cluster. So she started out with just a vanilla Kubernetes cluster, and she needed to do 3 things to do that. One is to actually add some nodes with GPUs to the cluster. That she does like adding any other node. So she just creates a server with a GPU and she adds it as a node to the cluster. Next, she needs a device plugin for the GPU that is running on this node. So you can kind of imagine it to be a driver for the GPU that exposes the resources that the GPU has to Kubernetes, so that Kubernetes can discover the GPU and it knows what are the capabilities of this node. Next, you don't want just any workload to run on this new node, right? You want it to be reserved for actual GPU workload. So what we do is we taint this new node. In this case, we're giving it an nvidia.com taint that tells the scheduler to not schedule anything on this cluster, except for if it's actually specified for this cluster. So now our cluster is ready to actually receive AI workload. And all we need to do for the pods that we schedule there is we need to tell them to actually use the GPU, and we need to add a toleration for this taint that we have previously created, right? So that the workload actually gets scheduled on these new GPU nodes. One easy thing, one easy thing that Chloe can now use to host her LLM on a Kubernetes cluster is Ollama. And luckily, luckily there is an Ollama Helm chart that Chloe can use. You can see a very minimalistic values.yaml file here, where you basically just specify the underlying GPU provider that you use, you enable it, and you tell it which models you want to run and you want to load. But things were very slow. Chloe was getting annoyed, and so were her customers. The responses from the LLMs from Ollama were very slow, and also running the whole thing was very expensive, because how she used the GPUs was not very efficient, right? She had one model per GPU server, and what she could do is she could partition the GPUs. So she could say this GPU can be used for multiple models and then split them up. But even after doing that, things were still very, very slow. And what we need to do to figure out this problem is we need to look at how LLMs actually work. How do they actually go through a prompt like this? So here's an example prompt. What is Hans's medical history? That's something that one of the customers of Chloe might ask her system. Now what the LLM does is it takes this as an input and it generates word by word the output of that, right? So it generates the first word, Hans, then it adds this new word also to memory, and it loops through the whole thing again. So it needs to, after every token, or kind of every word, it needs to input all of that again back into the LLM. So it takes the question and this word Hans, and it inputs it into the LLM again. It generates the next word, Hans has. Now it takes all of this and puts it back into the LLM. Generates the next word, Hans has very. Generates the next word, Hans has very severe, and so on. Hans has very severe arthritis. Now we know, but we needed to wait for quite a long time, and it needed to allocate all of the memory for this. Because at the beginning, the LLM doesn't know yet how long is the answer going to be, right? Because it generates it word by word. So it needs to allocate a lot of memory. Excuse me. Needs to allocate a lot of memory for the whole answer, because the answer could be very long or it could be very short. So what we end up having is the whole red part here. Thank you very much. The whole red part here is actually wasted in memory. And this causes a lot of costs, because basically only around 20 or 40, between 20 and 40% of our GPU are actually being used. The solution to this problem is called paged attention. So Chloe goes back to her desk, which has now upgraded a bit because she has made some money with her startup, but not that much. And she stumbles upon this solution called vLLM, which is an open source project that you can find on GitHub. I think it usually comes from UC Berkeley, and it has around 64,000 stars on GitHub by now. And it's a tool that you can use to run inference of LLMs on Kubernetes or on other hardware much more efficiently. And it does this paged attention, so it dynamically allocates the resources that your LLMs would use to generate the answers. And it also does a lot of other optimizations to run your workloads. There is also a Helm chart for this, which is called the vLLM production stack. And you can see more or less here how it's configured. So it's also a very simple values file. And by using that, Kubernetes will, on the one hand, split your LLM workload over many different nodes, and it will apply all of these optimizations that we have seen before. And by doing that, Chloe's startup gets very successful, and they win the Lampe Award, as you can see. So to do a quick summary of the 3 different approaches that we just saw, you can either run your LLMs or get them via the API. There, obviously, you don't have sovereignty. They're running just anywhere and you're giving up your data, but it's pretty production ready. So I recommend this for tools that don't tackle or that don't deal with sensitive data. Another approach that we saw was hosting our own Ollama, where we do have the sovereignty because we're hosting it ourselves, but it's not really production ready. You can use it for internal tools with low concurrency. But if you want to go bigger, if you want to host actual customer workload, then I really recommend to use something like vLLM. There you have all the sovereignty because you're hosting it on your own infrastructure, and it's very production ready because it scales all the way. And with that, I thank you very much for your attention.
Thank you for the presentation. So, Miriam, now it's